Okay, so if there are no questions, I'll start. So let me first review where we reached last time. So we wrote down the differential equation for lambda, and the equation took the following form: lambda dot square is k over a0 square here omega is the ratio of the actual density today to critical density, and the critical density was defined as 380 squared over 8 pi g. So this is just rewriting of the Friedman equation. Then he also said that we have omega m naught plus omega r naught plus omega lambda naught is equal to 1 up to experimental uncertainty. Okay, as far as I know, this is equal to 1. And now if we set today's time, set t equal to t naught, then lambda dot is h naught. Okay, so on this side you have h naught square here plus k over a0 square. On this side you have just h0 square, because this sum of this is 1. Right, so you see that you get h dot square plus k over a0 square equal to h0 square, and that's the argument that a0 must be very large. Right, so the fact that the total density is equal to the critical density within experimental accuracy means that a0 you can think of as infinity within experimental accuracy. So you cannot distinguish a0 from infinity. So from now on, we'll just set we set a0 equal to infinity, right? Which means k over a0 square equal to 0. Okay. And the important point that I had mentioned earlier, but let me say it again, is that this means that the right hand side is larger than this today, but it also means that it is larger than this in the past and in the future. Okay, because these numbers, omega r naught is small, but these are order 1 numbers, right? 0.3 and 0.7. Okay. So if lambda is smaller than 1, then this will dominate over this, right? Because this will become larger. If lambda is larger than 1, then this will dominate, right? And it's already large, so obviously in the future also it will be larger. Okay, so because of this, I can ignore this k over a0 square equal to term throughout the history of the universe. Okay, at least the ones that are based on this equation. So now we can use this to find how lambda changes as a function of time. Okay, so our equation now, let me write it again. So our equation is lambda dot square is h0 square times omega m0 over lambda plus omega r0 over lambda square. Okay. And I'm going to take a square root. So let me remove this and put a half. And you pick the positive sign of the square root because lambda dot is positive. Right? We know that lambda is increasing today. So you take the positive square root. And we had seen from our earlier analysis from the analogy with classical particle that lambda dot remains positive all through. So this now I can integrate. This gives you dt prime. Okay, or dt, let me write first. So dt is equal to d lambda h naught inverse d lambda over this whole thing Okay, and this I'll also write slightly simpler version. I'll just multiply by lambda in the numerator and denominator. Okay, I multiplied by lambda, both numerator and denominator, right? But in the denominator, it become after inside the square root, it become lambda square. Right? That's why you see multiplication by lambda square in the denominator. So we can now integrate this to find t as a function of lambda, and once we do that, we can invert it to find lambda as a function of t. Right? But for most purpose, as you'll see, the t as a function of lambda is good enough. So this tells us now integrate, and here I have to make a choice of what we choose as the origin of time. Right? So far we are saying that t naught is today's time, but of course this equation is invariant on a time transition. Right? We didn't fix the origin of time by any means. Okay? So today we are going to fix the origin of time by saying that this is the time at which lambda was 0. Right? So our definition of the origin is lambda equal to 0, right? Because that's where the universe becomes singular, right? The metric, because you have the lambda t square multiplying the spatial part, metric becomes singular. So we integrate here from 0 to t dt prime, which is nothing but t, and on this side you get H0 inverse integral 0 to lambda of t times lambda prime d lambda prime over yes lambda prime to the 4. Thank you. Is it clear? We're just integrating the simple equation. Because if you remember the form of the metric, it was minus dt square plus lambda t square times the spatial part. So at lambda equal to 0, right? The spatial part, that means you move in the coordinate, right? But you don't move, right? Because you don't travel any distance, right? Inverse of the metric will have a 1 over lambda square. Right? So when you actually calculate the Riemann tensor, you will find that it diverges, right? Or all scalars, some Riemann tensor square, for example, is all index contracted, you will find that it diverges. This is genuine singularity. Yeah, it cannot be removed by coordinate transformation. Right? For that, of course, you have to do this calculation, right? Take the Riemann tensor square, right? And you will find that it diverges. I mean, you can also see it in a different way, that the rows, right? It has powers of lambda in the denominator, right? Because rho m, for example, falls off as 1 over lambda cube, right? Rho radiation falls off as 1 over lambda to the 4 and so on. So the energy density diverges, right? And if the energy density diverges, then better be that the Riemann tensor diverges, right? Because on the Einstein's equation relates the R mu to the energy momentum tensor. Okay, so this is clear. Okay. So this determines t as a function of lambda, but also implicitly lambda as a function of t. Okay, we can integrate this numerically, right, to find t as a function of lambda, and then just turn the graph 90 degrees to find lambda as a function of t, right? So using that, we can determine how lambda will evolve as a function of t. Later on, we'll use some approximation to evaluate this in various ranges of lambda. But first, let's try to calculate the age of the universe, right, which is one of the important things. So age of the universe is the value of t today. This is the age measured by the co-moving observer, because we had seen that for the co-moving observer, t is a proper time. right? For the co-moving observer, the spatial part is not changing, and dt square coefficient is just 1, right, or -1. So t is the proper time. So the age of the universe as measured by a co-moving observer, t naught, is just integral 0 to 1 h naught inverse. Today lambda is 1, right? 0 to 1 lambda prime d lambda prime over now one thing you notice, this integral is perfectly convergent, right? Because there's no the possible divergence at lambda equal to 0 is not there, because the denominator actually goes to a finite constant, right? Because of this omega r naught term, right? So as lambda goes to 0, it actually is a convergent integral, right? So you can just put it on a computer and evaluate it. So let me remind you of the values. So this is roughly 0.3. This is roughly 0.10 to the -4, right? This actually plays no role in this age calculation, and this is 0.7 roughly, right? So if you put it in the computer, I think the result that you get is about 0.96. So this is omega lambda naught, 0.7. Right? Total is almost equal to 1. Right? So the matter is about 30%, cosmological constant, dark energy is 70%, radiation is negligible today. So now if we use the value of H0 that I gave, right, which is roughly say 70 kilometer per second per megaparsec, right, and you have to use the fact that the parsec is about 3 light years, right? I mean, I think the exact value is some 3.2 light years probably, right? You just put all those things in, and you can calculate this number, right? And you will find that this is roughly 1.4 times 10 to the 10 years. Because that is the age of the universe. Even in the early days, people were finding a larger age because H naught value, sorry, smaller age, right? Because H naught value was thought to be larger. And basically then that they ran into a puzzle because they found that there are some rocks whose age seems to be larger than the age of the universe, right? Which obviously couldn't be. Okay, so then they actually, so this, now everything is consistent, right? There is no known object in the universe whose age is larger than this. Okay, so at least there is a contradiction. So next, I'll introduce another concept which will be very useful, okay? And this is co-moving horizon. At time t, this is the distance or co-moving distance traveled by light from t equal to 0 to some time t. So it's of course is a function of time. Okay, from the beginning of the universe, right? Imagine that when the universe started, there is some light emitted from some point, and this measures how far the light would travel in co-moving coordinates in time t. Is the definition clear? Okay. Now, why is this important? Okay. It's important because the co-moving distance today, right, measures how far we can see, right? Because light travels that much, right? So you cannot see farther than that, right? The objects that are farther than that, their light wouldn't have reached us today, right? So that's why the co-moving horizon is important. Okay. And the calculation is very simple, right? So let me remind you of the matrix. So this is minus dt squared plus lambda t squared times d rho squared plus rho squared d omega squared. Okay, I have absorbed that a0 term in the scaling of r, right? So rho is really a0 r. So rho directly measures the co-moving distance. Okay. And we can assume that the light travels along a radial geodesy, right? Because of the homogeneity and isotropy, doesn't matter where you start and in which direction you go. Okay. So for simplicity, let's suppose that we start at the origin and you want to know how far light will travel. Okay, starting from the origin in a given time t. So for that, we set ds square equal to 0. Okay, and because it's going radially outward, okay, we set d theta and d phi equal to 0. This is for radially outward motion. So this tells us that dt, d rho is given by dt over lambda t. Now dt we have already expressed in terms of d lambda, right? The top equation. So you have to just divide it by lambda, right? So ultimately the equation that we'll get for rho is very similar to what we have here, except that one lambda will be absent, right? One part of lambda will be gone. Is that clear? Right? I just write dt in terms of d lambda using that. So this is given by d lambda over, so the lambda will not be there, right? The lambda will be cancelled because you are dividing by lambda, times omega m naught lambda plus omega r naught plus omega lambda naught lambda to the 4 to the power half. Okay. So this gives us the rho h of t as integral 0 to lambda. H0, thank you. H0 inverse. That's the only thing that scale sets the dimension, right? Everything else is dimensionless. So there is H0 inverse. So this is d lambda prime. Report 4. Thank you. Okay, exactly the same expression if the lambda prime gone, right? Because you are dividing by lambda prime. So again, we can put it on a computer and calculate this. So rho h today of t naught. How far can we see today? Will be obtained by setting lambda equal to 1. Right? Because today lambda is 1, right? By definition. And this one gives you 3.24 H0 inverse. So it's larger than the age of the universe. C has, we have set x at equal to 1, right? So light travels at speed 1. right? But what you see from here is that this is larger than the age of the universe, about 3 times larger, right? So this is about 45 billion light years. So 4.5, use the same measure, or 4.5 times 10 to the 10 years, light years. Okay, well, we may say light years because it's the distance, right? You multiply by, so c is hidden, right? So when you're measuring distance, you have to multiply by c, so the years become light years. So in a sense, we see that the signal seems to propagate faster than the speed of light, right? Light travels only about h naught inverse, this travels about 3 h naught inverse. Okay. But of course, we have not violated any principle of relativity, right? Because we are using Einstein's equation to make this conclusion. So basically, what happens is that it appears that it travels more distance because of the expansion of the universe, right? Light has its own motion in the vacuum, right? Minkowski space, light travels at speed of light, okay? But the universe as a whole is expanding, right? So that stretches out the how far light can proceed, right? And that's why we see this 3 times the distance that we can see. Yes. So that shouldn't change the speed of the light. Yeah, so intrinsically speed of the light is not changing. If you go to a local inertial frame, right, you will find that the speed of the light is 1. But if you sum it up over some curvature, you will see some. Exactly. Right? In this case, the curvature is not even in the spatial direction, right? It's basically because of the time evolution that we are saying this extra bit. Okay. Sometimes one also uses the notion of physical horizon, right? Which is that at time t, how much physical distance light would have traveled. Okay. And that is easy to calculate. It's not, used very much. But all you have to do is that the physical distance you can see is obtained by the multiplying d rho by lambda t, right? At any given time, the metric has this lambda t multiplied, the spatial distance. So to get the physical horizon, we just have to multiply rho h t by lambda. Okay, that's the physical distance at any given time, the physical distance that the light would have gone. But this is useful, right? We'll use the comoving horizon. Okay, for that, because it has some properties that we'll see will be useful. Yes. It will be the same, yes. In the past, right, the actual distance traveled, physical distance, would have been multiplied by lambda. So rho h t at a given time will give me distance traveled by light. That we will measure today. That is how far we can see, but there will be a factor of lambda t more. Yeah, that will be how far we can see in the comoving coordinates, right? Because you are calculating change in the comoving coordinate, right? The comoving coordinate is the physical distance today, right? Because today lambda is 1, right? So this spatial distance is really the d rho really measures the physical distance. In the past, there would have been a lambda t, right? Lambda would have been smaller. So in the past, if you want to calculate, so comoving horizon is given by this, right? How far in the rho space it will go. Okay? But if you want to know how far physical distance it would have traveled, that you have to multiply by this lambda t. Right? This is the physical distance measured in the metric at that time. It would have been smaller, exactly. Yeah, so it would have been smaller for 2 reasons. One is because this integral would have been smaller, right? Because lambda t doesn't go all the way to 1, right? It becomes less than 1. But it's also smaller because the universe, the stretching effect, right, hasn't happened fully, right? The lambda has not gone all the way to 1, so there is a scaling by lambda t that you have to do. dt square remains dt square, but the metric becomes singular. Yeah, because we argued that the Riemann tensor diverges, right? Because the energy densities diverge. If you look at the right hand side of the Einstein's equation, the energy densities diverge, right? So something has to diverge on the left hand side also. So lambda t equal to 0 is a genuine physical singularity. Okay, you can also calculate the Riemann tensor from here and check that the scalars are diverging. Okay, now we can ask also another question, right? That suppose today we send out a spaceship, right, and give it as much power as we can, right? Which basically means that let's suppose that a spaceship travels at the speed of light, right, or very close to the speed of light. How far can we go in the co-moving distance? Right? So how will you calculate that? We start today. We wait for as long as you want, right? Can you go to infinite distance or finite distance, right? Or how? Yeah, so you have to integrate basically exactly the same expression from 1 to infinity, right? Because today lambda is 1, we start today, right? And we go all the way to lambda equal to infinity. So this is something called a future horizon. So future horizon, that is how far can we travel? Again, in co-moving coordinate, in co-moving distance. Because the physical distance will be defined because the physical distance, the lambda is increasing, right? So that will stretch out the actual physical distance that you can travel. But let's look at the co-moving distance. So that is given by, I'll call it rho future. T0 is integral for H0 inverse, integral T0 to infinity, d lambda prime. Okay, not T0 1, because you are doing lambda integral, right? T0 would have been if we had written in terms of time coordinate. Lambda today is 1. So 1 to infinity, d lambda prime. This is also a finite integral. Right? It's a finite integral because for large lambda prime, right, this term is going to dominate. Right? The square root of that will go as 1 over lambda prime square, and d lambda prime over lambda prime square is a finite integral, right, for large lambda prime. So you can also put it in a computer, and the result that you get is 1.14. Exactly, because lambda goes to infinity, right? Lambda, it has to be multiplied by lambda t, and that will go to infinity. But the co-moving distance, right? Suppose you see some stars at some distance today, right? Can you reach there or not, right? You can ask, right? Because the stars are moving away from us. That's we are measuring only in the co-moving distance, right? And what we are saying is that today we can cover about 1/3 the distance that we can actually see, right? We can see up to a distance of, where did that go? 3.24, right? H0 inverse. But how far we can reach only up to this distance, right? So many of the stars that we see today, right? However hard we try, we can never reach. Okay, because of this constraint. And here, one important point to note is that this happens only because of the cosmological constant. If this term was not zero, not there, then you see that this integral would have diverged, right? Because then this will dominate. But d lambda prime over root lambda prime is a divergent integral at infinity, right? So in the absence of cosmological constant, you can go as far as you like. Okay, you can reach everything that you see. But because of the cosmological constant, right, our motion is limited, right? We can only reach certain distances. And that happens because cosmological constant essentially drives the expansion very fast. So the far away objects are moving away very fast, right? And that's why you cannot reach them. Because you are essentially competing your engine with the expansion of the universe, right? And the expansion of the universe wins if the cosmological constant is present. Is this clear? Yes. 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 But I mean, suppose you see some stars today and you see that we find that, okay, that's a nice livable star, right? Let's go there. If that star is beyond this distance, right, you'll never make it. Right? So the point is there are things that you can see, but you can never not reach. And they also cannot send signal, right? If someday the star just blows up, we'll never know, right? Because even the light signal cannot reach us from there. But we are seeing the star right now, but star was, what we are seeing is the what the star was in the past, right? So suppose today it blows up, right? That information will never reach us. So what will happen is that the star will just fade, right? Because because of the expansion of the universe, it will go further and further away from us, right? So it will just fade, and I mean, so we'll just see it fading. Okay, and so the point is that if you wait long enough, then what we'll have is that you have basically our local group of galaxies, right, which are bound, right? They will be there, right? But outside this local group of galaxies, everything will be outside our horizon, right? You can never see anything. Exactly, yeah. So that's what is driving this this fact, right? But again, it's just that number is not the important one, right? The fact that it's accelerating, that's the important part, right? Because this omega lambda naught is the one that is responsible for the acceleration. The fact that lambda dot is actually increasing with time. Well, it's understood in the same way that gravitational wave is understood, right? Everything is Einstein's equation. So this comes out as a solution to Einstein's equation, right? So it's the same, right? Because even gravitational waves, I mean, you have nonlinear effects, right? So you understand it not as in the way you will understand solutions to a linear equation. Okay, the other thing I just want to say, right? It's a somewhat trivial statement now, but it will be useful later. Is that this rho h, because of this form, right? That you integrate from 0 to lambda, right? That to calculate this, you can actually break up this integral into different parts, right? It can be thought of as the sum of different contributions, right? And in different parts, you may be able to use different approximations. So, and it's just a simple statement that an integral can be written as a sum of sub-integrals, right? Integrals over sub-regions. This one, if you multiply by lambda t, right, to get the physical horizon, then it's not the case, right? The physical horizons don't add because you have already multiplied by lambda t. Later on, right, you multiply by something else, right? So to get the physical horizon, you have to first divide by lambda t, right? Add and then multiply back by lambda t, right? So it's the rho h of t which gives us directly as a single integral, right? Without any extra time dependent factor in the front. Okay, we are going to make use of this, and that time it will become clear why it's useful. Okay, so far we have just not done any approximation. Well, of course, approximated this by 0.3 and 0.7, but that once you have better experimental accuracy, you can change those. Right? But now we are going to describe some analytic results. Right? And analytic results we can do not for a generic value of lambda, right? But for some ranges of lambda. Right? The ranges where only one of these three terms dominate. Okay. So we are going to start from very small lambda. Right? At very small lambda, which term dominates? If you look at this, see it's the same combination. The denominator combination is the same, right? In both there and here. So if you have small lambda, you can see that this is the dominant term, right? Because this has a lambda, this has lambda to the 4. Right? For small lambda, this is dominant. So small lambda, omega r naught dominates. But let's try to understand how small this lambda should be. Right? Because you see omega r naught is already very small, 10 to the minus 4. Right? This is of order 1. So as long as lambda prime is larger than 10 to the minus 4, this will still be larger than this. Right? Because this is 10 to the minus 4, this is of order 1, right? 0.3 we can approximate by 1 for this. So as long as lambda prime is larger than 10 to the minus 4, this will dominate. Okay, this of course is small. So we need lambda prime less than 10 to the minus 4, right? So small basically means the lambda is much less than 10 to the minus 4. In that case, in the entire range of integration, right, from 0 to lambda, here, the omega r naught will dominate. So in this case, we get t equal to integral 0 to lambda t, lambda prime d lambda prime over omega r naught to the half, which is lambda of t square over 2 omega r naught to the power half. Sorry, h naught inverse, I keep forgetting. H naught inverse. Okay, and you have used the lower limit lambda. So this tells us the lambda of t will be 2 omega r naught to the half h naught t to the power half. Okay, so basically it says that lambda goes as t to the half. That's the way it grows in the radiation dominated era. Okay, very early in the history of the universe. Let's also calculate rho h. That lambda prime is gone, so that's d lambda prime over omega r naught to the power half. So this gives you h naught inverse So by the way, I should have said this number 10 to the minus 4 okay, sometimes is denoted by lambda IQ. And this one, the corresponding value of T, okay, is called TEQ. This is the time at which the matter and radiation energy densities are equal. Right? That's where the transition from matter to radiation takes place, right? Above this lambda, matter was dominant, right? Below this lambda, radiation is dominant. So that's why it's called the equality, lambda equal. Okay, this is an important number. It's roughly 10 to the minus 4. Right? That's what you should remember. Or omega r naught, right? Roughly. So the radiation domination stops at lambda IQ, right? After lambda IQ, it goes to matter domination. Now, of course, you cannot use this formula, right, all the way to lambda IQ because matter has already started becoming important. But you can get a rough idea of how much the horizon size would have been simply by setting lambda equal to lambda IQ in this case. Okay, it's not exact, right? There are numerical, overall numerical factors because matter has already started contributing. But roughly, this is H naught inverse times omega r naught to the minus half times lambda EQ at TEQ. But lambda EQ is omega r naught, right? This is omega r naught. So this goes as H naught inverse times omega r naught to the half. Is it clear? So this goes as, let me write, H naught inverse times omega r naught to the power half. Because lambda EQ is omega r naught. Now omega r naught to the half is about 10 to the minus 2. So what it is saying is that at the end of the radiation dominated area, the co-moving horizon size was about 10 to the minus 2 H naught inverse. Right? Order of H naught inverse. Right? Or 3 times H naught inverse, doesn't matter. The order of H naught inverse. So that co-moving horizon size at the end of the radiation dominated area was much smaller than what it is today. Which means that most of the contribution to this integral, right? To calculate the co-moving horizon, we have to do an integral from 0 to 1. That in that contribution, right, the radiation dominated part contributed very little, about 1%, because it was 10 to the minus 2 H naught inverse. So if you want to get a rough estimate, we can just forget about the radiation part, right? Just use matter dominated matter and cosmological constant and get the answer. Okay, and you can explicitly check that the answer will not change very much, right? Because the contribution for radiation dominated area was small. Is this point clear? And this will be a general feature, right? That as lambda increases, right, most of the contribution comes from the large lambda region. Right? Today lambda is 1. If you consider a lambda which is say 0.01, right, which is well inside matter dominated area. Nevertheless, what you will find is that the contribution to the horizon when lambda is 0.01 is much smaller than the contribution to the horizon size today. Which means that most of the horizon contribution, most of the propagation of the light has happened between lambda equal to 0.01 and lambda equal to. Okay, this is a useful thing to keep in mind because we will see that this will make use of this.
So this is the point at which the Big Bang happened, and till what point the radiation is dominating. That time, how much is like that?
Exactly, that's right. And what you are finding is that till that time, the amount of time distance the light traveled, right, co-moving distance, is tiny compared to what it has traveled today. Okay, which is intuitively perhaps not, difficult to see because it has less time, right? Radiation dominated area existed for a very small range of lambda, right? So in that small range of lambda, it didn't travel very much. But we will see that this can be misleading, right? And that will be an important point. So it's something that something that you have to calculate and check.
Why this radiation dominated era? Universe has expanded its size to some 10 to the minus 4 times the what we have today.
Exactly. Exactly.
That's quite a big distance.
Yeah. So most of the expansion happened afterwards, right? but that expansion, of course, that distance got stretched out, right? So that's not a point, because whatever it had gone, right, that is getting stretched out anyway. But it's just that it didn't have enough time to go very far, right? Intrinsically also, light didn't have enough time to go very far. So there are two effects competing, right? One is the light is propagating. The other one is the universe is expanding, right? So the expansion of the universe, right, stretches out small distances to large distances, right? That will always happen, right? But it also goes to know how much light has actually traveled, right? That amount was small in the radiation dominated era, right? Because suppose light, it had already traveled half of the cone distance, right? Then the physical horizon at that time, of course, would have been much smaller, right? Scale by this factor of lambda. But that would have stretched out to today's today's distance anyway, right? That's by the expansion of the lambda of the universe.
So some of the
Yes.
matter and radiation.
Yes.
But all these equations that we have.
Yeah. So this formula that I have written here, right, is only approximate. In the radiation dominated era, up to radiation dominated era, you can argue that the matter and radiation would have very little coupling. The decoupling you can use, right? But way below lambda equal to 10 to the minus 4, right, there will be an exchange of energies, right? So this formula is not exactly valid, right? But there will be order 1 corrections to this. That will do in the next course, right? Not in for this course, you can just stop here, right? That below 10 to the minus 4, there is some physics, right? But you are just this is approximate, right? This number will be multiplied by maybe by a factor of 1, factor of order 1. Okay, because of this fact that there are different components which will exchange energies. But that effect will not be very much. You can estimate. Yeah, it's not very much, meaning it's multiplication by term of order 1, right? Term of order 1 may mean square root of 17, for example, right? Which is still, I mean, compared to this 10 to the minus 2 suppression, right? It's not much.
As we go to in this integral, as we go to lambda goes to 0. At that point, omega r as well as omega m is diverging.
Yes, but omega r is diverging, not omega r, but the radiation energy density diverges 1 over lambda to the 4. Matter energy density diverges 1 over lambda cube, right? So that's why radiation dominates. You are right that both are diverging, right? But the radiation is diverging faster.
At the very point of equal to 0, that is the. So at that point, all these divergences, there is nothing. This is the higher divergence. So that's
yeah, I agree. So we don't go, let's not go there, right? Let's start the evolution, right, from lambda equal to 10 to the minus 7. Okay, up to that point, you understand the physics very well. Right? So you can start from there, and it will be clear that okay, whatever the age of the universe you are saying or the horizon you are saying, right, is measured from that lambda equal to 10 to the minus 7 to today. Okay, don't go all the way to 0, because at 0, as you said, you don't really know what's happening. The time, well, I don't remember now, but you can convert it into seconds, right? It will be a few. I mean, 10 to the minus lambda equal to 10 to the minus 3, right? I think is about 400,000 light years. Okay, and then you have to convert it using this lambda equal to the proportional to the half formula, right? How much would have been? Or 400,000 years. I mean, you are talking about an age, right? Yeah, it was about 400,000 years old when lambda was 10 to the minus 3. 10 to the minus 3 is also an important number, which you'll see why.
point in time, this radiation was the cause of expansion.
Yes, indeed.
What sort of influence the initial condition had? For example, when I throw a ball, what initial velocity I give, that is an important factor.
Yes, so that is basically H naught. Yes, roughly you can say that is we are using the data today, right? But you can convert it to some initial condition there. Okay, now we go to matter dominated. So this is the case when lambda is between 10 to the minus 4 and 1. Because when lambda is much larger than 10 to the minus 4, it dominates radiation. And when lambda is much smaller than 1, it dominates the cosmological constant. Right? As you can see, right? Omega m naught multiplies lambda prime, omega lambda naught multiplies lambda prime to the 4, right? So when lambda prime is small, then the first one dominates. So in this region, the equation is integral u1 to t. I'll say what t is. U1 is so this is H0 inverse. So on this side you have t minus t1. This is lambda 1 over square root of lambda, so lambda to the half, lambda to the 3 half. Okay. So here T1, okay, lambda 1 and lambda are both supposed to be larger than 10 to the minus 4 and 1. Because you are using this in the whole range between T1 and T, right? Or between lambda 1 and lambda. Is it clear? Now T1 and lambda 1 are of course not independent, right? Because from the starting from the radiation dominated era, right? If you actually integrate, you will find a definite relation between lambda 1 and T1. Right? But for that you have to integrate that equation exactly, right? Through this matter radiation transition. But once you have gone far past, you can use this formula. So this tells us the lambda t to the half, 3 half, lambda to the t, okay, is equal to okay, I can just write the formula. So now the point is that if we take, if lambda t is much larger than lambda t1, okay, which basically also means t is much larger than t1. But to start with t1, already you would have to be larger than equality, right? Because we are using this formula. Now suppose lambda is much larger than lambda 1, then basically we can replace this by t and we can replace this by lambda 3 half, right? Because this is larger than that. Okay, so this tells us that lambda t is given by h naught t 3 by 2 square root of omega m naught to the power 2/3. Okay, so basically what I am doing is that using this approximation, I am ignoring these terms. So net upshot is that lambda goes as t to the half, t to the 2/3 in the matter dominated area. Right? In the radiation dominated area, lambda goes as t to the half. In the matter dominated area, lambda goes as t to the 3/2. Let's look at the horizon. DH. So what we will calculate, sorry, DH of T minus DH of T1. Sorry, we called it rho H, right? Rho H of T minus rho H of T1. Okay, rho H of T1, you have to calculate by integrating that equation, but let's calculate the difference between rho H of T and rho H of T1. In that case, we can use the this formula. Okay, except that there is no lambda prime. So this is integral lambda 1 to lambda E d lambda prime, and H naught inverse is as usual there, d lambda prime over square root of omega m naught lambda prime. So this gives you H naught inverse 1 over square root of omega m naught times 2 lambda t to the half minus lambda 1 to the half. Is it clear? So again, we see that if lambda is much larger than lambda 1, this is the dominant term. This term roughly is capturing the size of the horizon or of the order of the size of the horizon at time t1. This is the difference. Right? So suppose lambda 1 is 10 to the minus 3 for some reason, right? Let's suppose that you are interested in lambda 1 is 10 to the minus 3. In that case, at that time, the horizon side would have been of the order of 10 to the minus 3 by 2, because there is a square root. Right? Today the horizon, well, H naught inverse I am leaving out, omega m naught is of order 1, so you are leaving all those out. So the net point is that if we are calculated the horizon size at a time when lambda was 10 to the minus 3, it would have been 10 to the minus 3 by 2 times what it is today. Because in the matter dominated area, it's roughly growing as lambda to the half. Right? When lambda goes from 10 to the minus 3 to 1, the horizon size grows by a factor of 10 to the 3 by 2. Okay? So the horizon size at that time would have been smaller. Right? That's what is important, and also how much smaller you can figure out, it's square root, smaller by square root. So 10 to the minus 3 would have meant that the horizon size at that time was 10 to the minus 3 by 2 times today's horizon. Is this point clear? See, these are again order of magnitude estimate, right? All I am saying is that because the horizon grows as lambda to the half in a matter dominated area, if in the matter dominated era, if you want to compare the horizon size at T1 and horizon size at T, okay, you basically look at the factor of lambda and take the square root. Right? That's the factor by which the horizon size increases in the matter dominated era. Right? Now you can convert all of this into time, right? But for most purposes, we will not talk about time, right? For most of the cosmology, when you talk about some given epoch, right? When this happened, when that happened, right? You basically specify lambda. Okay, or as we'll learn later, you specify the temperature, which is more or less the same thing. Okay, not at what time it happened. Okay, you can answer that question because lambda t relation is known. Okay. But specifying lambda gives you more useful information than specifying the actual time. Is this clear? Are there questions? Okay, so now let's do the cosmological constant dominated era, which happens when lambda is much larger than 1. So this happens when lambda is much larger than 1, right? Which will be basically in the future, not today. So in this case, we can write. So let's suppose that lambda 2 and lambda are both much larger than, they're both much larger than 1. Okay, you have to start evolving from somewhere, right? And that time will take to be later by the cosmological. Well, this is not what is called T versus 0.7, right? So it is larger, but not very much larger. Right? In our epoch, if you want to do calculation, right? Accurate calculation, you have to keep the matter term. The radiation you can ignore, but the matter term you have to ignore, right? But by the time say lambda has doubled, right? Then the cosmological constant, of course, doesn't decay, right? Cosmological constant will remain the same. The matter density will fall by 1/8, right? So that 3:7 ratio will become 3:8:7 ratio, right? So by the time it has doubled, you can start using the cosmological constant dominated equation. Okay, so in this case, the equation becomes integral T2 to T dt prime is equal to H naught inverse so this is roughly d lambda prime over lambda prime. Okay, so this is H naught inverse over log lambda t over lambda 2. Okay, so now the dependence on initial condition cannot totally be ignored, right, because of this logarithmic dependence. So this tells us that lambda t is lambda 2 times exponential H naught t minus t2 1 over square root omega lambda naught. Okay, so roughly it's some constant times e to the h naught t exponential h naught over square root of omega lambda t. Okay, so the growth is exponential in the cosmological constant dominated era. Should you multiply root omega lambda naught? Oh, I'm just calling, oh, yeah, this omega lambda naught here. And I'm just calling this constant c. The h naught t2 1 over square root of omega lambda naught. Right? I'm just absorbing inside the lambda 2 to call. Oh, I see. Yeah, thank you. Yeah. Is it clear? And if you want to calculate rho h of t minus rho h of t2, this is not there. The lambda prime is not there, right? So you get h naught inverse 1 over square root of omega lambda naught. So 1 over lambda, d lambda over lambda square is what we are interested. Okay, lambda prime is not there. So that's 1 over lambda, right? So you'll get 1 over lambda 2 minus 1 over lambda t. Is it okay? So we see that as lambda goes to infinity, rho h of t approaches a finite value. Rho h doesn't increase. Right? It increases a little bit initially, but by the time it has expanded a lot, right, it has actually approached a finite value because lambda t goes to infinity, of course. Lambda t is growing exponentially, right? You can see. But this goes to finite value. But this is something I've already seen before, actually, because we calculated our future horizon, right? And we found that it's finite. How far we can go, right? And that this is basically reflected here, right? So our future horizon is finite because in the cosmological constant dominated era, okay, horizon side approaches a finite value. Expansion never stops. It continues to expand, but the co-moving horizon size approaches a finite value. And basically what happens is that this expansion is so fast, right, that the fact that you are traveling at the speed of light makes no difference, right? It's basically how much, whatever the universe stretches you is what you get, right? Because outsides are going very fast. So by your engine is of no use.
Should we say expansion is fast because that would
Yeah, no. So you shouldn't call it, think of it that way, right? Because the actual speed, right, you measure in local inertial term. That's still one. Okay, expansion is the co-moving distance is increasing, right? But that's not the speed, what you normally would call speed in inertial term. So if you want to travel very far, right, the most efficient way is to travel as far as you can today, right? Go as far as you can, and then just stay there, because then the expansion of the universe will take you far away, right? Then your traveling is not of much use. Okay, because the farther away you are, right, the faster you are moving away from each other, right? And at some point it doesn't help to travel, you just stay there. Okay, other questions? Yes, indeed. Well, that observable size is the past horizon, right? This is what we call how far you can access. Exactly. In the future, this much will be available to us. Right? For astrophysical purposes, it's the other one which is more important, right? The past horizon. How far can we see? Right? And that's about 45 billion light years. This is useful for those who want to build spaceships, right? And travel.
How old will that be?
That will be close to beginning. Right? See, as you will learn that we cannot see beyond lambda equal to 10 to the minus 3 anyway. Okay, but lambda equal to minus 3 surface is about 45 billion light years away. Right? Because the actual horizon contribution from beyond lambda equal to 10 to the minus 3 was a small amount compared to the actual past horizon. So if you take lambda equal to 10 to the minus 3, right, you can translate to time and you can also translate to distance. Right? The redshift of 1000. Right? Lambda equal to 10 to the minus 3 means redshift of 1000. That far is what we can see, and that's about 45 billion light years away. So this redshift is used both for distance to specify how far the object is, and also for time, right? How old the object is, because those are related. Right? At a given redshift, the object at a certain distance, or at, I mean, if you see some object at a certain distance, then their age at that time is also fixed, right? Because light is traveling from there to here.
But a single object won't be enough, right?
Yes. So the ones that you see at 10 to the minus 3, right, are the homogeneous ones, right? And that is the microwave background, right? We'll discuss now the origin of the microwave background, right? And those are coming from redshift of 10 to the minus 3. Sorry, redshift of 10 to 1000, right, which is lambda of 10 to the minus 3. Yes.
This mismatch in the numbers, the age of the universe being some 14 billion years, and the horizon size has become some 45 billion years. Can you just explain once more, because that's not fair.
Yeah, it's counterintuitive, right? It is happening because the universe is expanding, right? It's stretching. The light is traveling at the speed of light, but at the same time, there is a stretching going on, right? And it's the combined effect of these two that makes you think that you have traveled farther than what speed of light will allow.
Physical length.
Physical length.
Not co-moving distance, physical distance.
No, today, when you're observing these distant objects, right, their physical distance from us today, if you measure in today's slice, is 45 billion light years.
I find that if you, instead of calculating lower physical distance, then the integral, you can have a lambda t also in that. That would then be just.
But physical distance, okay, that is not really, I mean, anything physical, no? I mean, what will you, what does that distance mean? See, if you want a geodesic distance, right, that is of course 0 because you are measuring light path, right? ds is 0 along the light path. Right? So multiplying this by lambda t and integrating, right, doesn't really give anything physical. Yeah, but integrating that is not not something which is physical, right? It's not really a distance in any sense.
For example, let's consider a set of points, right? Consider 2 points here and here. So each and every point is expanding from respect to each other. Like
Yes.
points are going away from each other, and we start light from point. It has to reach this point and we have to expand, but they can't really expand before light gets from here.
Or do they cannot expand? They can. That's why you cannot reach the far away objects, right?
Discretely, this wouldn't make sense. Only if you have continuous set of points, only then this expansion will take.
Well, I don't even know how to make sense of discrete things, because if it's discrete, then what is the light path, right? That has to go through a continuum. See, the point is that even if you don't move, suppose you are not interested in sending light ray, right? You just stay there. You're getting stretched, right? And that is the effect which is adding to it. Right? You can examine the equations and you can convince yourself that this is what happens, right? Then in the equations, you have never violated any law of relativity, right? You have used the fact that light travels along null rays.
Integrating from 0 to our time is giving some 45. But what we are now saying is that from here onwards, if we calculate how much the light can
Go.
that will be limited.
Yes, that will be 14 billion. Or no, 40. Yeah, that roughly. Yeah, 15 or 16. Yeah.
So, and my confusion is just.
So total distance that the light travels in the whole age of the universe is 45 plus this, from 0 to infinity.
Starting from here to we are integrating to infinity. So it is like infinite proper time, like infinite age of the universe.
Well, see, proper time depends on what geodesic you are using, right? What trajectory you are using. If you use a light trajectory, it is 0, right? In 0 proper time, you reach from the Big Bang to the age of the universe, end of the universe, right? So it's so one has to think of it. In the light of general relativity, right? Often the usual intuitions fail. Right? That's why the co-moving distance, right, is something that is from our perspective. That's what is useful. Right? And we will see that we will use this co-moving distance. As long as you understand what it means, right, there should be no confusion. Right? And we are going to make use of this co-moving distance to describe a puzzle, which the puzzle, of course, exists independent of what formalism you use. Right? But a co-moving distance is a useful concept, right? That basically says that given an object, a co-moving object, how far it is along the spatial slice. Right? Nobody can travel along the spatial slice, right? Because that's a space like geodesic along which you are measuring the distance.
Observe radiation from that has not reached us.
10 to the minus 3. As we will see that 10 to the minus 3 is a lambda value from which you can observe the radiation. And the CMB is coming from there. Yeah, there is a reason why you cannot see past that region. Okay, so let me then begin the next topic, which is the thermal history. Right. So far, we have not talked about temperature, right? Except that once we mentioned that 2.73 Kelvin is the current temperature of the microwave background. Right. Otherwise, we are only dealing with metrics and distances. But now let's look at the thermal history. So today's temperature is 2.73 Kelvin. Now, Kelvin is not a very useful unit for describing the temperature, right, in the early universe. Instead, what we specify, which is entirely equivalent, is the Boltzmann constant Kb times T, that has the unit of energy, right? And that we measured, we can use any energy unit that you want, but we will measure it in electron volts. So the Boltzmann constant Kb basically allows you to convert from Kelvin to electron volts. So this is 8.62 times 10 to the minus 5 electron volt per Kelvin. So Kb T naught, okay, you can just multiply, is roughly 2.5 times 10 to the minus 4 electron volt. Okay, so when you say that today the universe has a temperature of 2.5 times 10 to the minus 4 electron volt, we basically mean that KBT value today is 2.5 times 10 to the minus 4 electron volt. Is it okay? Microwave background temperature. The CMB that we see microwave background coming from all directions, right? That has a black body spectrum, and this T naught is that temperature, right? So we use this value of T naught to calculate the energy density today using sigma T to the 4. Well, no, you don't talk about matter and radiation. Matter is separate. The radiation that is coming from the stars has very little energy, right? This is what you are observing. If you keep a microwave detector, right, you will find that there is radiation coming from all directions, right? Uniform background. You have to of course subtract of the background, right? All the radiation microwave that is produced in the earth and in the nearby regions, right? Then after you subtract those out, you find that there is a radiation of 2.73 Kelvin, right? Black body spectrum coming from all directions. That's the radiation. Temperature of the radiation is 2.73 Kelvin. Right? So the Planck distribution formula depends on the temperature, right? You remember the Planck distribution formula, which tells you how much energy is there per unit frequency band. Right? That depends on the temperature. So what you observe, the frequency distribution of radiation fits this temperature.
How do we subtract?
Subtract?
You said we have to subtract the microwave
Well, I mean, go very far away so that the other sources are small, right? And then you see how much the dependency is, right? For example, that you know that if it's terrestrial, right? If you go far from the radio source, it will fall off as some 1 over r, right? So you try to go far away and see how much it's falling off. You know, the way it was discovered, right? It was discovered not because people are looking for microwave background, people are trying to do something else, right? And they found that their detector was not working because it always had this noise, right? And that noise turned out to be this microwave background. Now you have to do more work, right, to cut it off. I mean, now the best is to go to space, right? And then you measure the microwave background. Because this is there everywhere, right? Even in space, I mean, the point is then in space, things are a little better because you still have a lot of radiation in the plane of the galaxy. But you can look out away from the plane of the galaxy, right? And there the noise is much less, right? So you can, so now the microwave is the signal, right? And you try to cut out other things as noise.
we assume that matter is entirely
Yes. Yeah. We assume matter is entirely cold. Exactly. The microwave radiation. So now we know that the density of radiation goes as sigma T to the 4. Right? This is the statistical mechanics. So if you have a black body with temperature T, right? Energy density goes as sigma T to some constant times T to the 4. We have also seen that in cosmology, rho r goes as rho r naught over lambda to the 4. Okay. So this means that the temperature of the microwave radiation in the past would have been T naught over lambda. Right, because lambda to the 4 will become lambda T naught to the 4 divided by, sorry, sigma T to T naught to the 4 divided by lambda 2. So this is saying that in the past the universe was hotter. In fact, you can do better. I mean, this is just only average energy density. If you take the Planck's formula, right, the black body radiation formula, and there if you use the fact that the radiation frequencies are getting stretched, right, because of the redshift, you will find that you reproduce. If you assume that the today's distribution is the Planck black body formula, you can show that in the past the distribution would have been again the Planck's black body formula, but with a different temperature. Okay, basically the point is that the non-trivial part of the formula is this exponential of minus h nu over 10. Right? So if you scale nu, and effectively that corresponds to scaling t. Okay, and that gives you this temperature. So the upshot is that the temperature of the microwave background was hotter in the past. Is clear? So if at lambda equal to 10 to the minus 5, say, I just chose lambda equal to 10 to the minus 5. The temperature would have been 10 to the 5 times more, right? So T would have been 10 to the 5 times T naught, but T naught is given here. That's 25 electron volt. Is clear? Now something happens at 13.6 electron volts. Remember what happens at 13.6 electron volt? Hydrogen ionizes, right? So if the temperature was 25 electron volt, right, then the hydrogen would have been ionized, right? Whatever hydrogen you have, in fact, most of the universe is hydrogen, right? And some part is helium, right? Mostly it's hydrogen and helium. Okay, helium ionization is hard, but hydrogen would have been ionized. So which means that the universe would have been in the form of a plasma. Okay. Charged particles moving around. Okay, and when charged particles move around, right, the photons scatter very efficiently, right? Because photon couples to charge. Okay, the photons would have scattered efficiently. So if you start from that time, right, early universe, and see what happens as the universe is cooling, as it's expanding, it's cooling, right? In the early universe, the photons would have scattered very frequently, right? And this is captured by saying that the universe was opaque at that time. Okay, the mean free path of a photon was very small. Once the electrons and protons combine into hydrogen, okay, then the universe becomes neutral. And when the universe becomes neutral, essentially the photons can travel freely. So after hydrogen ionizes, okay, the universe becomes neutral and the photons travel freely, and that's what we can see. So if you just buy this argument, it would seem that at lambda equal to 10 to the minus 5, or maybe at around by lambda equal to 10 to the minus 4, right, when the temperature has come to 2.5 electron volt, universe would have become neutral. In actual practice, right, I mean, for this you have to do a little more statistical mechanics. What one can show, the universe actually becomes neutral at lambda equal to 10 to the minus 3, which is later, right? Not lambda equal to 10 to the minus 4, okay, at lambda equal to 10 to the minus 3. And the cosmic microwave background that we are seeing, we are basically coming from that era. Once lambda became larger than 10 to the minus 3, right, the photons started traveling freely. And the cosmic microwave background essentially is giving us the image of the universe at 10 to the minus 3.
say this lambda of order 10 power minus 5, then it is a very permanent. There is not enough matter. There enough matter to scatter. Whatever matter will be there, that will scatter. But is there enough matter to scatter all that?
There is enough. Yeah, you are right that there is less matter than radiation, but there is still enough matter to scatter. Right? Because the point is the matter density is very low. Right? I mean, okay, this is something we will not use in this course. If you take the ratio of the value of the photons to electrons, right? There are 10 to the 9 photons per electron. Okay, so it's really low matter density. But nevertheless, the once you have charged particle, right, the cross section goes up so much that even that low density of electrons is enough to make the universe opaque. Okay, it's only when they combine, right, then the scattering stops. Okay, so we'll discuss this next time in some more detail, right? And then we'll see that this feature that the microwave background gives you the image of the universe at 10 to the minus lambda equal to 10 to the minus 3, okay, will lead to a puzzle in cosmology. Right? There's something that we cannot explain. What that thing is, we'll see tomorrow. Well, there are photons, but the photons are scattering very fast.
But we cannot see those photons now.
See the photons that we are seeing here, right? Last scattered at 10 to the minus 3. Before that, of course, those photons would have been there, right? They are just moving around, scattering from the electrons. But the information that they had gets wiped out, right? Because they keep scattering. After 10 to the minus, when lambda became 10 to the minus 3, right? And the universe become transparent, then those photons are traveling to us without any further scattering. Yeah, that's the sense in which CMB gives the image of the universe at 10 to the minus 3, at lambda equal to 10 to the minus 3, right? But those photons may have been existing for a while, right? They are just scattering away with the electrons before that. Right? But that information will be lost because there are so many scattering, right? I mean, you lose the history. Yeah, matter dominated era began at 10 to the minus 4. So we are already well into the matter dominated era at 10 to the minus 3. So this last scattering, so this surface is called last scattering surface. That what you are seeing from today, right, forms a surface in the sky. There's no physical surface. It's just that that's the surface from which the photons are coming. Right? So the last scattering surface, right, is well into the matter dominated era, because lambda has become 10 to minus 3. That's about 10 times the value of lambda where matter starts dominating. This fact will not be very important for the qualitative understanding, but of course it's important for quantitative calculation, that the fact that you have gone into the matter dominated era. We can, that will be in the next course, right? I mean, we can not only comment on such things, we can also calculate exactly what will be the ratio of hydrogen to helium, for example, right, in the universe, and other elements. If the expansion was slower, well, you cannot just make the expansion slow, right? Because I mean, it has to satisfy Einstein's equation, right? So what do you want to make slow? The H naught. Yeah, so then things you can work out what it will be, right? How things will change if H naught was different.
So what people as CMB today is the entire trapped radiation escape.
Exactly. Which escaped at lambda equal to 10 to minus 3. Right? The point is, I mean, it is not a surface. It's beyond that time, right? Before that time, the whole universe was opaque. Right? At that time, the universe becomes transparent. Right? It's just that what you are seeing, right? I mean, the photons that you are seeing today are coming from a surface at that time. Okay, so we'll continue tomorrow.
All the calculations that we are doing, isotropy is there embedded in this all the calculations. So when lambda is small, are the calculations still valid? Because then the systems will be bounded by their gravity. Is it still homogeneous and isotropic?
Yeah, the point is it is still homogeneous and isotropic. In fact, one can show that the universe was more homogeneous and isotropic for smaller lambda, right? I mean, because we can see the image of the CMB, right? That tells you how homogeneous and isotropic the universe was at that time, right? And CMB is really highly homogeneous and isotropic because you can see in different directions, right? So the whole region of the universe that we see was homogeneous and isotropic.
What changed? How it become so?
That's because of the gravity, because of the small inhomogeneity, right? What happens in the gravitational thing, small inhomogeneity, there is a little overdense region, right? Then that starts pulling more matter, right? And that's what causes the inhomogeneities. So the idea is that whatever fluctuation in the CMB we see today, right, is what caused all the formation of stars and galaxies, etc. In fact, this was also a puzzle for a while because people knew that CMB was very uniform, right? People had found CMB to be very uniform, and they are puzzling about that if you start from that uniform universe, right? How did structure form? And they had already predicted that if the inhomogeneity was less than 1 in 10 to the 5, then you couldn't explain how the structure formed. And it turned out that the inhomogeneity was exactly 1 in 10 to the 5. Right? So it was not inconsistent with structure formation, but it's just barely enough. It's what we see.
For this T going as 1 by lambda with ground distribution.
Yeah, so first you can see just from the total energy density. The Planck distribution, you write down the Planck distribution form, right? Which is a function of h nu over t. That's a non-trivial part, right? And then we use the fact that the nu, right, in the early universe was larger, right? Because what we are seeing today is smaller, but that's the higher frequency, right? And the higher frequency was basically scaled by lambda. Because the formula involves nu over t. H and T are of course constants, right? So if you scale nu, that is equivalent to scaling T. It will be as if you have the same distribution formula, with a different. Like the power that is contained between nu and nu plus mu. You have been contained between nu over lambda and nu